Continuing our look at the inverse trig functions, this video is going to deal with composite functions that contain an inverse trig function. Our objective, find the exact value of a composite function containing an inverse trigonometric function. So what do we know that's going to be useful for this lesson? Well, we know the definitions of sine, cosine, and tangent. We know our unit circle trig values. We know what a composite function is. A composite function is a function that is a combination of two or more simpler functions. Composite, compose. We know what an inverse function is, a function that undoes a given function. And we know that our inverse functions, inverse sine, inverse cosine, and inverse tangent, are restricted because we don't want to have more than one possible answer. Okay, so our ranges are restricted for the inverse sine function to between negative pi over 2 and pi over 2, to the inverse cosine function to be between 0 and pi, and to the inverse tangent function to be between negative pi over 2 and pi over 2. So when we evaluate when we look at a composite function, okay, we want to evaluate the inside function first, and then we'll use that value to evaluate the outside function. We'll need to draw a right triangle for angles that we don't have exact values for. And we will do an example of that as our second example, example number 2. So let's take a look at example number 1 here. Evaluate exactly, if possible, the expression, the cosine of the inverse sine of 0.5. So this is the inside function. We're going to take the inverse sine of 0.5 first, and this is the outside function. We will then take the cosine of that answer. So let's do the inside function first. The inside function says, find the inverse sine of 0.5. Well, I'm going to rewrite that because on our unit circle, we're used to seeing it as a fraction, maybe make it a little bit more visible on our unit circle. This is identical to the inverse sine of 1/2. Okay, so we're looking for an angle whose y value is 1/2, and that angle needs to be between negative pi over 2 and pi over 2. So we go to here, and we look between, if I get my paper straight on there for you, we look between negative pi over 2 and pi over 2, and we find which one has the y value of 1/2, and it's right here, and that angle is pi over 6. Okay, I'm going to use radians here. That's pi over 6. Okay, so we've evaluated the inside function. The inverse sine of 1/2 is pi over 6. So now we're going to use that value in the outside function. Okay, what is the cosine of pi over 6? So this value now goes into here. Well, that's another one we know. We know pi over 6. Heck, we were just there. So we'll go back to here. We'll find pi over 6. Pi over 6 is, we weren't just there, we were in the right quadrant, I should say. Pi over 6 is here. What is the cosine of pi over 6? Well, that's the x value, which is the square root of 3 over 2. And so this is root 3 over 2. So the cosine of the inverse sine of 0.5 is equivalent to root 3 over 2. Okay, the cosine of the inverse sine of 0.5, or 1/2, is equal to the square root of 3 over 2. We can check that with Desmos. Of course, it's going to be an approximation, and that's okay. We'll go back into here, and we'll do the, we'll put that left side. So functions, I want to take the cosine of the inverse sine. So go back to functions and choose the inverse sine of 0.5. Okay, and I can close the parentheses, and I come up with an answer of 0.866, etc. That's the left side. Is that the same as root 3 over 2? I'm going to create a fraction bar first. Put the square root of 3 in the numerator and the number 2 in the denominator, and you can see those are identical. Okay, those are approximations out to like the trillionth place here or something. So we're good. We got the correct answer. Now let's do an example for which we don't have the exact value for the inverse, and we want to use the right triangle to come up with the exact value. Evaluate exactly, if possible, the cosine of the inverse tangent of 9. Okay, so the inside function, okay, this is the inside, this is the outside. The inside function says, what is the inverse tangent of 9? Well, that's not a value we know from our unit circle. So let's draw a right triangle. Let's remember, okay, let's recall that the tangent is equal to the opposite over the adjacent. Okay, I'm going to write this as a fraction, and that's equal to 9 over 1. Okay, so we can draw a triangle. We're looking for this angle so we can solve this first part. And the tangent is 9 over 1, so this is 9 over 1. I'm going to make that a right triangle. And now we know the angle. This is whatever this angle is here. And I want to find the cosine. I want to find the cosine of that angle. Okay, well, the cosine, of course, is adjacent over hypotenuse. Okay, well, I have the adjacent. That's 1. I can find the hypotenuse. Okay, the hypotenuse using the Pythagorean theorem. This is the square root of 9 squared minus 1 squared, which is the square root of 9 squared plus 1 squared, excuse me, plus 1 squared. I made a mistake there. The square root of a squared plus b squared is the square root of 82. So the cosine of the angle is the adjacent over the hypotenuse, which is 1 over the square root of 82. If you want to rationalize the denominator, we would multiply this by 1, written in the form root 82 over root 82. That's a 1. And the answer with the denominator rationalized is the square root of 82 over 82. So when you don't know the exact answers, what you can do is create a right triangle and then use the right triangle to come up with the value of the outer function.